I guess time is short, so we should probably get going, right?
Okay, good.
Yeah.
All right, so let's get going. I guess I'm up here, so I'll take the honors, and it is an honor and a privilege to introduce, one of a rather esteemed alums. I was thrilled to hear that Nathan was coming back because Nathan was, a shining presence when he was a student among us here during a certain heyday several years ago. Nathan graduated from Oneonta in 2019. And during his time here, Nathan was somebody who I think really took advantage of all the opportunities that we offer here by doing independent studies and projects and engaging himself. And I felt fortunate. I got to work with Nathan closely, working with subjects in quantum field theory and supersymmetry and things like that. And I loved working with Nathan. It was amazing to watch somebody like him who could just absorb things and mainly have an enthusiasm for it all, and a desire to know, a desire to learn. That's the most important thing. You really want to know and learn physics, and Nathan exemplified that greatly. And so he's continued. Nathan is now a PhD student at the University of New Hampshire. I'm assuming that the generalized topic is like astrophysics, cosmology.
Theoretical astroparticle physics.
Yes, he's doing theoretical astroparticle physics. Topical field these days. It really sounds incredible. I know he's doing some great work, and he's going to tell you about it. And and I guess I should also say it was a great surprise. Nathan came back and he brought with him, some of his cohorts graduated. Both Hannah and Melissa, who are both back there, graduated also in 2019. Also, really wonderful students, and it's so nice to see them all come back. And hopefully someday you guys can feel the same and want to come back and visit us again. So again, it's a great pleasure, and I will turn it over to you, Nathan.
Thanks, Mike. Appreciate it. All right. Time for the actual show to begin. Okay, so yeah, let's just have me reflect on my life during and after SUNY Oneonta. So I didn't take this lovely picture. I'm using this lovely picture because right now we're in the thick of the woods. All right, so that's what I was trying to metaphorically and symbolically show by showing this like thick forestry. All right, so first coming to SUNY Oneonta, I was a chemistry major. I was a singular major. I guess I gotta let somebody in. Now they're in. Okay. Another Nathan. So that's awesome that they're able to make it. So yeah, I came in as a chemistry major, and then for the first year and change, I did, I just did chemistry. And then I took physics 1 and physics 2 with the one and only Hugh Gallagher in the back. I took actually a large percentage of my physics curriculum under Hugh, at least the main staples, including E&M, thermodynamics, and who knows what, energy and society and other things, stuff like that. I bothered him constantly. So one day in physics 2, I came up to him and I said, I wanted to be a physics major. And he said, okay, you should go talk to Mike Fox. And I was like, because I was telling him I was like watching some like documentary about like string theory or something like that. And then I went to Mike Fox and said, I want to do physics and I'm interested in, theoretical physics. He's like, do you know what supersymmetry is? And I was like, no. He's like, do you know what symmetry is? And I was like, no. I know, circles are symmetrical, but that's all I really know. And then from then on, I was a physics major, and then I decided the brilliant idea that math was a good part of it too. So I did that as well. So the first thing I want to show everyone are my points of contact. So you can contact me at any point in time if you have any questions about what I do, graduate school, life after graduating and such. If you want someone to talk to, you're more than welcome to email me at any point in time. If you don't feel like writing it now, I can just write it on the board or something, or you can talk to Hugh or Mike. They have my email, so and Josh as well. So yeah, all right. So now let's talk about life during SUNY Oneonta, right? Okay. First, it started out pretty bland. There's nothing going on. And then I encountered my lovely partner in crime, Melissa Mary. She's in the background. This is us at graduation. And then I had plenty of good times with my good friend Hannah Olds here. We would often go to her apartment and have plenty of good dinners and do homework. And then in the corner is also an alum who unfortunately couldn't make it, Stephen Atala. I grew pretty close with him towards the end of my tenure here. So that's a picture of all of us. And then my good friend and the latest speaker, actually, Jose Figueroa. So I'm very close with him. And so SUNY Oneonta was a blast having him around. And we had a good time with Hugh Gallagher. Hopefully the volume works, but it doesn't. But he's making a beat as we're learning how to count in thermodynamics, saying tick, boom, tick, tick, boom. Ooh, I like that. I'm going to keep doing this. And then just proceeded to essentially ignore the class. I'm not, saying you should film your professors without them knowing, but this was a key part of my career. And now to shout yet another professor who is infamous for the Oneonta Illuminati in his lovely triangles. It seemed like for a period of time, that's what he drew when he was talking about types of supersymmetries in string theory, which Hannah caught yet again when he was introducing this to prospective students in the room next door. So this was happening right in this building. All that history, y'all got to miss out on. And then one last fun video is one of the nights I was studying in the room over there, and I was wearing my socks, and that was it, and it was cold. And I left my ID in 121, so I had to call SUNY Oneonta police through the red phone to ask them to let me in. And Melissa filmed me during that as well. And I was talking to them, trying to explain the situation, that it wasn't an emergency. I just needed to be let in so I could go home. Yes, and my mom was coming to pick me up, apparently. And then one final thing. So during my time at SUNY Oneonta, because I started major late, I had to endure a semester or two with 20+ credit hours. Do I recommend such things? No, I do not. Your mental health will suffer a lot. However, what I did want to point out was the fact what Mike was talking about with my independent studies. I highly recommend that everyone at least tries at least one. You get to learn something that you wouldn't normally learn through the normal standard physics curriculum, which I think is a bonus, especially for folks coming from a liberal arts college like this one, because schools who are much larger than us and have very large physics departments get to offer a lot more courses than we do. So, for example, it's very standard for a lot of physics majors to go through 2 semesters of E&M, 2 semesters of quantum, and sometimes 2 semesters of classical mechanics. Where here you only have 1 of each. So you're already kind of at a disadvantage in that way. However, if you take these independent studies, you can get exposed to other things that you normally wouldn't. And this is going to help you in the long run, especially as you get into graduate school and want to start doing research in something. And the professors, are always open to talk to you about those types of things. And I did a lot with Mike Fox, to do with quantum field theory 1. And then I did a little bit of representation theory in the math department with Dr. Jonathan Brown, if you ever got the pleasure of meeting him. So after SUNY Oneonta, things were a bit rough. I was rejected by all 10 graduate schools in which I applied to the first time around. And I got the pleasure of working for Coca-Cola, the largest plastic polluter in the world, for a year. Those times were pretty rough because I was, going through a patch in which, I felt fairly alone because I got to see a lot of my cohort move on into other things, and where I was kind of told no. And, that had a lasting impact on me, but in a positive way after some time. So during this period, I went through a lot of self-reflection, and I, seeked a lot of advice, especially towards my tenure at Oneonta, from Dr. Fox and Dr. Gallagher, about what I should do with my life, because these things, unfortunately, when you apply to graduate school and PhD programs, is not necessarily uncommon. Sorry, but it does happen, and so yeah. Also during this time, I was working long shifts at Coca-Cola, and I was also self-studying general relativity to try to improve my chances to get back into graduate school during the second round. So after that, I just wanted to point out how many acceptances I got and how many rejections I received, just to show you how how the odds are stacked against you in a way. So the first time, as I said, was over 10, and the next time I went 2 for 10. So I just wanted to show you a quick glimpse of a rejection letter. The only one I could find was from the University of Minnesota. But I did want to show you like what they necessarily entail and what they, really typically say. They just say, we carefully, cover your application and well, we can't accept you and that's it. They just give you this short thing. However, when you're accepted, you get like a 2-page response about how much they like you. So yeah, I did just want to point out those two things because, applying to PhD programs is becoming more competitive. But I also, in this talk, I don't want to just get your hopes down and say this is hard. You won't get it. It's unlikely. I want to try to give you some hope at the end of the day. But I did want to point out some of the realities that you will face. So just some quick lessons learned from those 2 stages of my life. There comes a point in life where you might be forced to look inward, reflect. There's often a pill that's hard to swallow. That's something I had to do after my tenure at Oneana. However, sometimes you just have to make it happen. All right. So, I didn't feel like I was going to be able to make it happen the first time around. And then, after some good discussions with close friends and the professors here at SUNY Oneana, I, realized I'm going to make it happen and I'm going to do whatever I can to make it happen. So I decided to say, it might not be pretty when you make it happen. It's not going to be elegant. It's not going to look good. But sometimes you're going to have to require more sheer self-determination than what you think is possible for yourself. I promise it's within you. You just have to push the right button, and that fire will be ignited in the way. And I did want to quote from somebody in the room who I did pick on initially, but I do have a quote from him that stuck with me for a long time. Anything worth having is not easy to get. It's something Mike Fox iterated time and time again throughout my SUNY Oneana career. And I'm sure he didn't say that just to me, but that's something that sticks with me even to this day. I think about it often, especially when, graduate school is also very difficult and has met even different challenges. So, even when you, get to the point where you want to get, things still aren't necessarily easy. And so you got to remember some good quotes from folks you meet from down the line. And that's something that stuck with me time and time again. And I did want to point that out, that your professors can be inspirational too. All right. So part 2, graduate school. Right. So just to give you a quick glimpse of what graduate school is like, some of you can't read that, but this is my statistical mechanics exam that took me 26 hours to do on 4 problems. So you will spend an ungodly amount of time on a singular exam. Now, the reason why we were asked to time this was because the last one, folks, were spending 40. And we had to adjust that because obviously you can't be spending an entire work week and then trying to do your other duties on top of that, because then you're just endlessly working. We're more aware about, mental health and work-life balances. So I did want to have a nice little comedic / sad part of the graduate school. You will spend a lot of time staring at things. So things will be a little bit different in that way, where you do a problem now, it might take you a couple hours to sort out, generally, but here it's going to take you about, 8 or so. This is, you can't see it because it looked better on the computer screen, but this is just one of the scrapboard things that I had done for one of my homeworks, and I thought I wanted to show it to you all that, you'll make a lot of scrap notes as you're doing your work. You're not going to be able to just stare at a problem and be like, I know what to do. Like, I need to write down the free body diagram or whatever. You're going to have to stare at it and then read through the textbook and then stare at it and then write something down and be like, well, that was wrong. Let me stare at my textbook again and then keep going for hours on end. And, that took me, like 8 hours to figure out or something like that. I can't quite remember. All right. However, along the way, I met some really close friends. Those are 3 of them in my cohort. We were definitely dug in the trenches in graduate school. You spend a lot of time doing homework. Okay. You have weekly assignments. And I don't know if you have them here, weekly assignments, but those weekly assignments will take you a long, long time. All right. But you need folks along the way to help get you through. Collaboration in graduate school is encouraged. Having folks to, do the suffering with you is makes it a little bit more bearable in some sense. So yeah, I just want to show a few pictures, and then I just want to show another thing, some scrap work I was trying to do, and writing all over the board, and I think this was some calculation I was doing for a stress energy tensor, and for my research or general relativity or something like that. I don't quite know. All right, so now the question is, what is graduate school? What is it all about? What do you do? Well, So usually you have to pass an exam or exams, depending on what institution you're at, on advanced undergraduate material. So at UNH, you have to pass an entrance exam known as the qualifier on the 5 main topics. That includes quantum mechanics, includes electromagnetism, modern physics, statistical mechanics, and classical mechanics. The way it goes at UNH, you have 2 hours per exam, 1 day each. So you have to do it in that time frame. And then the faculty will grade you anonymously, so you can't write your name on it. But they have an identifier for you, so you can figure that out. So, and then some schools will, either have an additional exam for you to do. This is yet another qualifier exam, but this time it's on your your graduate material. Normally the core 4, quantum mechanics, E&M, statistical mechanics, classical mechanics. Fortunately, at UNH, we don't have that. So that's a good thing because you're forced with 1 exam. However, there is a supplement. You can't just get away scot-free and just say you're in the PhD program. You now have to do a thesis proposal defense. So this is where you have to show that you know your stuff on your research and you know the ins and outs of the respective topics that are covered within your research. So mine, it's particle physics and astrophysics simultaneously. So I have to know quantum field theory, and I also have to know general relativity. And have to know my stuff with my committee, because there'll be about 5 people, including my advisor, who get to grill me for an hour straight, single-handedly, all by themselves. They just get me and they get to just go at it for an hour after I do a talk in front of everybody, the entire department. Typically, your typical course load is taking 2 to 3 classes a semester, which might not seem like a lot, but 3 classes is about as much as you can probably bear, I promise. Unless you happen to be really good at some of your classes, but 2 is probably plenty, and that's what a lot of people do. I've done 3 classes twice, and I never wish to repeat those two instances ever again. A lot of late nights, 7 days a week, Monday through Sunday, all the time, every time, thinking about my homework assignments. On top of that, while you're taking your classes, you will probably have to be a TA, which is actually really fun. It doesn't, the TA might sound boring because you're not doing the research, but it's really fun to, get to sit down with some undergraduates on some basic physics, so physics 1 or physics 2. And you get to, teach them stuff. You get to do labs with them. You kind of grow a bond with them as you get to know them over the semester. And it becomes a really enjoyable experience. And I hope that, everyone, if they do go to graduate school, they do get an experience to be a TA at one point or another, because it had a profound impact on me. So yeah, while you're doing your research, so really what depends on whether you're a TA or an RA is whether your advisor has money when you find your advisor. So in physics, it works a little bit differently. You're not just handed an advisor upon entrance to graduate school, you have to go search for one. And you have to pass their own little exam, possibly, depending on who they are. For my advisor, I had to do some general relativity calculation with calculating stuff for neutron star interiors to make a little point. Because sometimes advisors do that when they have 5 students who want to work with them. You can't just say I want all of you, because now you have to fund students for X amount of tens of thousands of dollars a year. So you can only pick one, typically, unless you're not in theory. So if you're in space science or experimentalists, chances are you might have some more money to accept more than 1 student, but that's not always the case. So yeah, as I said, weekly assignments need to take 15 hours per. So the classes you got to take in graduate school, you got to do 2 semesters of quantum mechanics. So and then you got to do 2 semesters of E&M, and you also have to do 1 semester on math methods, which is basically, if you weren't a math major and if you weren't a dual major, this is all the math you need to know to do the physics. So you're just going to get a nice crash course for a whole semester about complex analysis and Green's functions and all sorts of fancy dancy things. You get 1 semester of mechanics, which is my least favorite. I thoroughly disenjoyed that. And then you have 4 electives. And what was I going to say about these? So what do all these classes entail, at least the ones that you recognize? Basically take all your undergraduate stuff, and now you're going to do it again, but now harder. You're gonna eliminate a lot of the assumptions. So like in quantum mechanics, you get the nice, finite square well. That's an entrance problem. You're going to be asked to do that on the first day. And then the next, you're going to be, writing down path integrals and doing a Feynman formulation for whatever that is, right? You have to learn a different notation. So, in Griffiths, when you all take quantum mechanics, you're going to be writing down wave functions all the time. Really, what modern quantum mechanics does is write things in Dirac notation. So this is a fancy notation to do some linear algebra stuff. But you really get a crash course on stuff, and it becomes a little bit overwhelming. So anyways, you're searching for an advisor. So I came into UNH, wanted to do string theory because I'd worked with Mike and I was so enthused about string theory and this, that, the other. And then I was a little bit turned off after meeting the string theorists at UNH. Not on his own doing. I just realized it was a lot more of a math research area than it was necessarily a physics research area. And I wasn't that inspired by what they were doing. So I was like, okay, I got to go look for someone else. So first I went to the quantum gravity person and I thought that would be a good idea. And he was like, he's not taking any students. I was like, well, okay, let's go to the condensed matter person. They're not taking anybody. And then I went to my current advisor now, Chanda Prescott Weinstein. She recently wrote a book, which I recommend you read, called The Disordered Cosmos. I really recommend it. It's awesome. And she was like, yeah, you can join my group. And I lucked out. So another thing I want to point out, if you want to do theory, this might sound a little bit glim, but it might be a little bit luck-based because, money, but, the squeaky wheel gets the oil. So, be a little pestering if you want to work with a certain somebody, and you'll find a way to it. I promise it will happen eventually. And then during the summer, so you don't get the summers off anymore. Now it's a full-time job. You either are TAing, depending on whether your advisor has any money or something like that, or you're doing research, which I've luckily gotten the opportunity to do these past 2 summers, which resulted in my first publication, which I'm going to briefly talk about at some point. Okay, so what do you get to do in graduate school? Well, you get to write proposals for money. All right, here are 3 instances in which I've had one of them I wrote all by myself, and then these 2 were mainly done by my advisor, but I did a lot of the science stuff. So when you're looking for money, you got to write. And I know, maybe some folks have chosen physics because they're not good at writing. Well, I'm sorry to tell you, you're probably going to have to learn how to write. It's a little bit more fun in the writing. So now you're not, talking about literary devices and stuff. You're actually going to talk about your own research. However, you got to clearly convey it such that someone who's very far outside your field can understand what you're doing and understand the importance of what you're doing. So for me, that's a lot of exoplanet researchers who are going to be potentially reading the proposals, and I need to make sure that they understand what I'm talking about. I can't just, talk about it like they know what I've been doing, because that's easy to do when you're staring at things for hours in a day. You sometimes forget that other people don't see it every day like you do, and then you say something that sounds obvious to you, but it's not necessarily actually obvious because you stared at it for who knows how long. What in terms of writing, what else are you doing? You are writing papers. This is my first publication on the archive. It's in, and we have the first version up now. So if you look up on the archive, which I recommend you do. So during your physics tenure, I would probably recommend looking up on the archive. It's free to access papers that you can get. You can talk about them with your professors, and they can help you learn a lot about what is actually going on. 1, in the physics field of your choosing that you want to know about. And 2, it can help you see the writing styles of professional physicists, and can help you with your writing as well, especially in the technical writing term, which is something I struggle with. So the amount of drafts I had for this paper on the first try was about 20. All right, and then I sent it in to be reviewed, and then they gave me more stuff to do. 24 points to be exact that I'm currently addressing, and I hope to wrap up tomorrow so we can be actually in a published journal, because this you don't need to be published to go on. So, yeah, some lovely lessons learned that I got in terms of classes and stuff like that. Find a homework and study group early. Chances are you're going to need it. You can't do graduate school homework alone. And having others, as I said, who will hold you accountable is key. And they make the best of friends. They're very close to my heart now, and I'm so glad that I got the opportunity to meet them and work with them closely and go through things like that. Second thing, and this applies right now, actually, don't be shy by answering questions in class, even if you're wrong. I do it all the time. oftentimes, and Hugh can attest to this, I would raise my hand, I would say something totally outlandish, and you'd be like, no, but I answered. And you know what? I learned something from that. That's wrong. So now I won't answer that on the test or the homework. So we can go further with that. And I also think, it adds a different level of engagement in the classes, especially with yourself and others, because they can see how you're thinking. And even if it's wrong, it's okay, because you know what? You're wrong more times than you're right, especially as you get further down the line. It's okay to be wrong. So yeah, another thing that applies right now, go to every single office hour that you can. Really, it really makes an impact, even in graduate school. One, building a bond with your professors is invaluable, not just because they're your superiors, also because down the line they can help you as you progress into life and do whatever you want to do. They can offer insights, they can give you awesome wisdom, as I was mentioning earlier. Pay attention to your writing now, not later, all right? And take it seriously. So when you're doing a lab report, take that very seriously and make sure that your language is clear and concise, such that if you were to hand that to, for example, I don't know, a biology major, and they read it and they say, I know exactly what you did. That's how you know your writing is where it needs to be. It's not just writing down equations and making a plot and saying, I understand this, I understand whatever. Now I want to quote someone I also picked on early on, but he had wonderful quotes. And I don't think he was necessarily talking about graduate school when he said the first quote, but graduate school isn't for the faint of heart. What he meant by that was, it's going to be hard. All right, you want to do this. This is where you want to go. You're still going to struggle. And I think this also applies to anything that you might want to do after SUNY Oneonta, whether it's, applying for jobs. Applying for jobs is hard. I don't know if Jose mentioned in his last talk, he told me he did like 80 applications and got like 4, something along those lines. So, just remember that after this, it's not for the faint of heart, but if you're truly impassioned by something, that's okay. You're willing to endure such things because, as Mike Fox was saying, anything that's worth having is not easy to get. And second, this one really, really got me through, especially as I was doing 7 days a week and taking classes. Take time to enjoy the work. And this may even apply now, right? You have a heavy semester, you have all these classes and all these assignments to do. And sometimes, and I even find it with myself, you get caught in this loop of, well, I need to get this done. I need to get that done. Let me get this objective done. I'm not really thinking about what I'm doing. And I'm just trying to get it done. Really take time to sit down and enjoy the work, because really it's a privilege to do what you're doing, honestly. And getting a chance to understand the world, the way it works, even if it's at a surface level, I think it's really worth it. And it also helps when you're struggling too. If you're having a hard time with your work and you're having struggles and things aren't necessarily working out. Okay, so what is research like? What is that? So, you read a lot of old and current papers. I could open up a file on my laptop, or 2 files. That's probably 100 PDFs long about all the papers that I have read and need to read. You will do a lot of reading, but that's good. And so you can even do that now. You can read papers on the archive and you can learn to digest papers in a nice, clean, methodical way. Sometimes when you're reading those papers, you go to some old textbook that you can find online or that your advisor has and you try to figure out what they did. You're writing up your notes all the time. If you're trying, when you're doing your research, there's a lot of things you do in any given day. It's probably good to write them down because it's good keeping track of what you've done, what you haven't done. And also it's good to remind yourself of the successes and failures that you experienced, because oftentimes in graduate school, you may feel like you don't belong there, because graduate school is really, really good about making you feel bad about yourself. It's not great about that. However, when you write down your notes, I have found that to be very helpful in reminding things that I have actually accomplished, because the human brain is wired to look at the negative and not necessarily the positive. So this is a good way to refocus on other stuff. There's many trial and errors with getting something to work out in research. I have some things that I've been working on that sound simple and like easy enough to do, and it doesn't work. And the thing I'm like, oh, then this should work, and now it doesn't, and I'm like, why? And then it's this constant back and forth. There's a lot of failures that go along with that. It's often slow going, and then suddenly you figure out the issue. You may have been stuck on something for months, if not weeks on end, And then for some reason you do one simple thing and it all just magically works now, like a code. I'm sure Dr. Nullenberg can attest to that right now as he's coding up some fluid dynamical simulations. There's a lot of time spent at a blackboard, staring at a code, a piece of paper, wondering why something's not working out. And you ask yourself what is going on all the time, even if like you're at a point and you just don't know what to do after that. Sometimes you just get to that point and you don't know what to do. It's not that nothing's wrong. You just don't know how to proceed. And that is also another struggle that you do in research. And what you do is you work with collaborators. In my case, I work with some folks at the University of Amsterdam, and we meet them weekly to talk about what we're doing to maintain a strong connection. So now to talk about what I do. The infamous asymmetric dark matter and neutron stars. Does anybody know what a neutron star is? Except you. We got a few in the room. All right, so neutron star is the coolest kind of dead star, right? You have our sun won't do the thing it needs to do to become a neutron star, unfortunately. Although I think it would be really cool if it did, because we're going to die anyways, so we might as well. Really, neutron stars appear when you have a really massive star, roughly about 8 times the mass of our own sun. And during this period, it will go into supernova explosion, and that core will condense down to the point where it cannot condense any further. At this rate, you form a neutron star. Neutron stars are the densest known objects in the universe outside of black holes. So see them if you want to see something more dense, but neutron stars, those are neutron stars. Dense little objects. To give you a grip on their mass and their size, they can be roughly around 1 to 2 times the mass of the sun. Theoretical limits place it at 3, but we haven't observed any that much. So I think the most massive is like 2.35. And their radii, or their diameters, I'll go with their diameter. The diameter is roughly that of Manhattan. So take our sun and crunch it down to the size of Manhattan. That is a neutron star. This is where gravity gets very, very intense because of its compactness. And I haven't mentioned what dark matter is yet for a reason. So dark matter. All right. So way back yonder, back in like 60s or 70s or something of that order. I don't quite know the actual decade when they were looking at the radial rotational velocity distribution of galaxies. And, the theory said, it should, make this nice little red curve. And when astronomers went out and started measuring these distributions, they got something that went up like they thought, and then it just flattened out. So the question is, what's there, right? So there's 2 answers to this question. You either say that Einstein's theory of gravity needs to be changed, there's something that we're missing, or that galaxy has a lot more mass than we think it does. And so, hence, dark matter. Dark matter is all the stuff in the universe that we don't know, all right? So just to give you a glimpse of what a galaxy looks like with and without dark matter. So the left one is without and the right one is with. You can clearly see a difference between the two. Or you won't. Much different. And the reason why this is actually important is because if they're not spinning at that rate towards their edge of their arms, they will actually not be able to sustain themselves and basically rip themselves apart. And we won't have the galaxies we see today. So we need something. So that is dark matter. Dark matter is something in the universe between dark matter and dark energy that makes up most of the universe today. In particular, dark matter is roughly about 5 times more abundant than the visible matter you see around you. Dark matter is so ambiguous, there is a boatload of theories in this lovely bubble made by Tim Tate over at UC Irvine. And there's a bunch of them. There's so many theories because it's so vague, it's so not understood. However, there's a certain class of theories known as asymmetric dark matter, what I look at. This is motivated by the observation by that mass density that it's roughly only 5 times. In terms of a theorist's point of view, that's not a lot. That's awfully close. So if they're awfully close, then that means at some point in the universe, we have a little bit of an asymmetry between dark matter and anti-dark matter, right? This is similar to those who know a little bit of early universe cosmology, where there was a baryon asymmetry, or visible matter asymmetry. There was a lot of visible matter, just enough to cancel out the anti-visible matter, and then the excess is what we see today. Same thing with this asymmetric dark matter theory. We have a bunch of dark matter asymmetrically aligned with anti-dark matter, and they annihilate in the excess. Dark matter is what we see in the present universe. So that's asymmetric dark matter. You just learned something very cool. All right, a specific case of asymmetric dark matter. So those who will eventually go on to take on statistical mechanics, you will learn that there's two types of particles in the world. There's bosons and there's fermions. How do you tell the difference? You learn about this thing called spin. All right, bosons have integer spin. That's, I won't tell you about fermions, it's half integer spin, whatever that quantity spin is for those who don't know what that is. All right, so bosonic model. It describes a bosonic particle with self-repulsion. Okay, so it's not like, it's like having protons and protons being near each other and they repel. Okay, so how does this repulsion come about? So forces aren't necessarily this instantaneous thing that you feel. It might feel like that based on your own experience, but that's not exactly how they go about. The way forces actually work in the realm of particle physics is that they exchange something known as a force carrier. This has a fancy term called a vector gauge boson. If you ever want to sound fancy, you can say that E&M is mediated by a vector gauge boson. It's a very fancy way you want to wow somebody. But this is a force carrier. What does that force carrier do? Between the two dark matter particles, so in this case, the chi is the dark matter particle and the force carrier is the psi mu. As they approach each other, they exchange that particle. All right, and what that particle does is exchange momentum between the two. And the momentum will determine whether they're attracted or repulsed. In this case, it's repulsed. All right, so the reason why I care about repulsion, I'll explain in just a moment, because that's needed for the whole neutron star thing. They can be attractive, but if you have a boson inside of a neutron star, basically what happens without the self-repulsion, the bosons can't hold themselves in against the gravity, and you generate a black hole inside the neutron star and you kill it. And we probably wouldn't see any neutron stars if there were bosonic asymmetric dark matter with no self-repulsion in them. So we need those. So how do neutron stars come into all of this? Well, come to find out, the interior of neutron stars is really uncertain. Worse, it's an active research today. It's part of what I do. So here you have this little figure. They've managed to cut open a neutron star by some luck in some way. They look into it and they still don't know what the hell is going on. The microphysical behavior of the ultra-dense neutron-rich matter. So neutron stars get their name because they're basically a bunch of neutrons because of that dense. The neutron pressure is what's holding them from collapsing. There's a little bit more going on in there, but that's generally what's holding them up. So these neutrons, because it's so uncertain, at these ultra-high densities, to give you a grip of how dense they are, they're about as dense as an atomic nuclei. So that means they have a density of times 10 to the 17 kilograms per meter cubed. That's stupid dense. So that means they can contain these exotic states of the matter. So there's a couple I want to introduce you to, known as deconfined quarks. So quarks are little things that make up protons. And normally in nature, you don't find them away from other quarks. They're normally in pairs or threesomes. However, there is a proposition that you could deconfine them at such high densities and that would break apart their interactions between the two. Or there's these fancy particles known as hyperons. So a hyperon is a fancy particle where instead of you have the typical quarks, if you know what a proton is made of, you have up and down quarks, you now tack on a strange quark, and that's a hyperon. All right. So the effects of these components can be characterized by this thing known as an equation of state. Now, an equation of state is something we're all familiar with, believe it or not. The ideal gas law is an equation of state, PV equals NKT. That is an equation of state. It's a way of relating pressure and density. In that case, you have temperature. It's a temperature dependence as well, but a lot of them deal with pressure and density. So this is a relation between the two, and that is an equation of state. The equation of state tells you what the neutron star is effectively made of. And then you can kind of theoretically construct one using that and make these lovely things known as mass radii diagrams. So the equation of state is effectively captured by these things known as mass radius diagrams, which are really just plots where you, given an equation of state, you plot all stable configurations of the neutron star of the mass and the radii such that it doesn't collapse. So you get all these fancy parts. But what I wanted to show here is I have these fancy parts for known neutron stars that have been measured by NASA in terms of their collaboration with NICER. NICER is a collaboration known as the Neutron Star Interior Composition Explorer. And so these are some of their mass and radii measurements to date. And as you can see, some of the mass and radii fall in all the bubbles, which means that they should check out with other neutron stars, and others don't. So that means that equation of state, which is deduced by the mass and radii, can probably be ruled out. And then I just gave you a bunch of little examples. I have fancy little acronyms, but it's not the here nor there for people to pay attention.
So those ovals are like regions in the space that are consistent with some experiments.
Right. Hmm?
So since there's two different regions that don't overlap, there has to be something wrong.
What do you mean?
Like that pink oval, for example, is not consistent with the purple oval.
Right. Well, because those are different measurements for different stars. Yeah. So this is PSR J0740.
Oh, okay.
Yeah. And then this corresponds to that. So this is a confidence interval on that measurement of different neutron stars. Yeah. Not a dumb question. There's no such thing as a dumb question. There's only questions I can answer and questions that I can't answer. And I can answer that question for you, actually. All right. So how do dark matter and neutron stars play along with each other? Dark matter can accumulate in two spots. One, inside the core. All right. So that means inside the interior of the neutron star, dark matter can accumulate there. So what does it do? It reduces the mass. I added gravitational for those who are going to be nitpicky about that term, but don't worry about it. If you don't, that's fine. You can reduce the mass and the radius. So this orange line that you see here is just a normal neutron star mass radius curve given some equation state. I throw in dark matter, I effectively reduce the mass and the radius by a sizable and measurable percentage, actually. When you accumulate enough of it, roughly around 7%, you can get reductions in the mass about 6 to 7%, reduction in the radii about 3%.
And you're referring to the baryonic mass in this case.
Yes. Yep. So the measured mass of the star.
So does dark matter have negative mass?
No, it does not.
Just that the mass of the dark matter plus the baryons is the same as the baryonic mass.
Yeah, right.
The original baryon.
Exactly. Can accumulate in the next obvious region. It can envelop the star. This is known as a halo, which is an extended dark matter structure that extends through and beyond. I tacked on this term baryonic surface. Baryons are just visible matter. I should have put visible matter, so I didn't confuse anybody, but I didn't think about that writing this morning. So you have a halo, and what the halo will do is effectively increase the mass, but not necessarily the radius. So the reason why it doesn't increase the radius is because dark matter is invisible. Right? It's not this dark substance, it's invisible. So nobody can see it. All we can see is its gravitational impact on things. So really, we would still measure the radius of the actual neutron star and not the halo. So, but because that extended structure exists outside the star, the leaving light from the star can be changed by the mass of the halo. That'll modify our possible measurements through this fancy term known as ray tracing. So how do I study all this? I can't just, generate all these mass radii diagrams and come up with, conclusions about dark matter. I can't do that. It's not a nice methodical way to do it. It's very crude. So you do something known as Bayesian statistics to study those two. But the first question is, what is Bayesian statistics? So we all know about the classic school of thought and probability theory, which is the frequentist interpretation about probability theory. So this says that probability is the relative frequency of events in the long run. Imagine just taking, flipping a coin. You can repeat that experiment over and over again, and you can talk about the probability of whether you're going to get heads or tails, right? So just to give you a quick scenario, I wanted to read the repeated sentence, but I didn't. But okay, so this is great for talking about lottery draws or coin flips, all right? Reflects the frequency of events occurring. However, an inappropriate question asked the frequentist is, what are the chances it's going to rain tomorrow? Tomorrow is only a once measured event. You can't repeat it, therefore a frequentist can't answer such a thing. Frequentists also don't worry about uncertainties in things like the mass of Saturn, right? The mass of Saturn is pretty certain, but our uncertainty in the mass of it is not. And that's a question you can ask someone who does the Bayesian interpretation. So Bayesian interpretation is really the modern interpretation of probability theory. This is essentially a model of uncertainty and allows for probabilities to be used quantitatively to deal with randomness and uncertainty. So getting measurements of mass, or you can also ask the Bayesian statistician, what is the probability it's going to rain tomorrow? So way the Bayesian theory works is you actually take into account what you know. This is known as the prior or your hypothesis. You can ask about the probability of that hypothesis. You can do such things in that type of measurement. So yeah, this is just a way of expressing uncertainties in our knowledge about stuff. So it's valid to consider probabilities of rain on a certain day in the mass of Saturn. So using the Bayesian statistics, you can generate these lovely things. Those who attended previous talks may have seen such a thing. This is known as a corner plot. Corner plot is a way of showing the Bayesian results for all the different parameters you worry about. So in this case, these are my dark matter models. And so you probably can't see it way back there, but if you have a variable plotted against another variable, you get a two-dimensional probability density plot. And the darker regions tell you how likely a certain combination of the value is, and the lighter regions tell you how unlikely a certain combination is. So light means unlikely, dark means very likely. And then when you have a variable plotted with itself, you get a one-dimensional probability distribution shown there, which can tell you whether it's constrainable or not. So here, in these two variables, whatever they need to be, they're unconstrained because there's no defined peak. However, here we see a peak towards the end, which tells us that that can be well constrained to a certain percentage of it, of that actual distribution. And then over here, this is another thing one can do. So taking this, you can make an equation state plot. So this is where you plot the pressure. In this case, we did the log because the pressures inside neutron stars are very, very high. So it's best to do log plots of such things against the density. And what we can see here is that when you include asymmetric dark matter in your analysis for neutron stars equation state, you actually broaden bands. So the orange band is the asymmetric dark matter piece, and then the lighter bands are where you aren't considering that in your analysis. And you can see that dark matter effectively widens it. So dark matter actually makes our constraints on the neutron stars a little bit less strict than what they are currently. Okay, so time to wrap up this fun time. Key takeaways about research. All right, it's a long and slow process. You're working on a novel idea though, and you're working towards answering questions which haven't been answered yet. And that's an exciting thing. You're actually working towards being a world leader in what you're doing. And that's small niche little area, but that's still special nonetheless. You'll fail more times than you will succeed. As I had mentioned earlier, you're gonna fail a lot. That's okay. That's part of research. You're answering a question no one has answered before. So there is no answer for you yet. You have to figure that out. And that's going to require a methodical and sometimes a methodical approach, and sometimes a little bit of luck involved as well. Because sometimes something just works and you're not quite sure why, and then you have to go back and figure out why. Lastly, research is not always a solo act. This is a little bit of a problem in academia. Sometimes there's folks who don't like collaborating, and it becomes this toxic environment where they seek to one-up other people and not make it so collaborative and take away their ideas in the research. That's something that I hope can not be in the culture going forward, but we have to work slowly one by one, each of us trying to collaborate with one another. It's not a competition. We're just trying to do this for the greater good of science. And I know some of this comes out because the pool of money is so small, but it still shouldn't be the case. We should always have a level of decency. Also, in my opinion, a collaboration gives a variety of perspectives, right? And that variety of perspectives can really make your results seem more sound. Because if a nuclear physicist and an astronomer and a particle physicist all agree on the same thing, the community is less likely to doubt you, all right? A particle physicist saying something outlandish, the nuclear physicist says, wait, that doesn't necessarily work. We're not really going to believe your results. So having more people involved in looking at your work and working with you actually is going to make your results more sound. And lastly, never, ever give up. The answer is waiting for someone to discover it. So why can't it be you? And with that, we're out of the woods. And this is a picture I took at one of the mountains, Franconia Ridge, up in New Hampshire, on one of the several hikes I've done there. So now you're out of the woods. And thank you for having my talk. I know that was a lot. Yeah.
Earlier you mentioned about making a method for reading through research or scientific papers.
Mm-hmm.
What do you mean by that?
Making a method for it?
Making them, making it easier to digest them.
Yeah, so what I like to do, now this is something you're gonna have to experiment with as you read them, because this is definitely a preference thing. First time I read it, I just read it. I read the abstract, read the intro, and I don't try to take any notes. I read it like a book. Really, the things you want to pay attention to are the abstract, intro, and conclusion. Those are the things that are going to get you where you want to go if it happens to be relevant. This is going to save you a lot of time in just reading a paper and realizing it doesn't actually mean anything to you. So just read those few things. And if you're still interested, now go back through and start making highlights. All right, you can do this on like your laptop. I do it all the time. And sometimes I even add in another little bit. So I like putting a legend on top. I make one color, the highlights, another color of things I need to, one, go check, or two, learn. So sometimes they have words in there that I don't know, and I need to go learn what those words and why they're saying those things. And so I go through, and now I make my highlights. Then the second time I go through, the third time I go through now, I like writing up my notes on it. So I like summarizing the papers and getting good results, because oftentimes your highlights are helpful after you've read it, but once you've gone back and read it, they might not be so helpful anymore. So writing up and summarizing the papers can give you a nice reminder of what those things are going to be like if you go and look, as you're writing your own paper, you're trying to cite somebody else's work, just to make sure you give them the appropriate citation. So, yeah. Yeah. Q.
A lot of what you talked about involves, in terms of learning, figuring things out, involves collaboration.
Mhm.
Can come in many different forms.
Again.
But it's sometimes hard to know how to start those collaborations.
Mhm.
How did that happen for you in grad school?
Yeah, so I had started my research with my advisor, Chanda, and she said, if you're going to do this, you're going to need folks to work with. And she happened to know a few people. And she said, I would like you to construct an email, telling them what you're doing, what would you like to do, and asking if they were interested in working with you. And then, of course, CCing your advisor with it and then sending it out. So a lot of it is just going out there and asking people and just seeing what they're going to say. And luckily we got some folks at the University of Amsterdam who Chanda knew well, that we lucked out with. So we already had that type of connection. But yeah, just reaching out, I think, is your best approach. It seems intimidating because you don't know these folks, but what's the worst they're going to tell you? No. So you just go in, and I mean, you get told no all the time. I mean, I got told no plenty of times. So, I mean, a no from one person doesn't really bother me so much anymore. So I'll just ask the next person. And if you run out of options, then I guess that might be an indication of maybe you do need to work alone, because the field is, not, I don't want to say it's toxic, but maybe it's toxic in that way, where they don't want to work together, because those things are important.
I just wanted to point out that sometimes you get a no because the person might be busy on something.
As well, yeah, true.
So you might get a yes later.
Right. They might say, hold off, keep working, we'll talk later. But sometimes you will have to remind them, because they can forget. It's easy, very easy to forget with all the things folks got going on these days.
Does the same apply for collaborations, for example, coursework?
100%. 100%. Just ask people. That's how I formed mine. I said, hey, do you want to work on the assignment with me? I'm really stuck. I don't know what I'm doing. Can you help? I'm scared. And, eventually I formed a nice little group, especially in graduate school. When people first get there, they're very open in that way. They might be a little shy, but if you're not the shy one, you can have at it and go for it. Yeah. Paul?
Could you please go back to slide approximately 40%?
40%.
You wrote things about succeeding in school.
There?
Yeah, that's the one.
Yeah.
So even though study groups and asking questions and answering questions in class and going to office hours and learning to write and being bold are important in grad school, You think they might be important in undergrad too?
100%, all the way through. I really do think having all of those things wherever you go academically is important, actually. So another thing I would add to the undergraduates in the class, sometimes even if you don't have a homework assignment to do, going back and looking at old, lectures or looking at the textbook and trying to work out something that you're all uncertain about, like really just formulating your own little exam. Be like, I don't know how to do this. I'm really uncertain about this and this and this. Let's go through and try to work it out on our own. And you can even go ask the professors, like, hey, can you help me with this? Like we were trying to, sort this out because, we think this might be something on the exam or something like that, or it might be on the next homework or whatever. Can you help us out? We're really stuck here. Even if you wrote down the first thing and you didn't know what to do after that, that's okay. It's fine. So it's a matter of trying and failing and going and until it finally cracks. Because eventually, if you stare at it enough, something in the back of your mind is going to be like, I finally see the grand picture. You might be looking into the forest and you're like, I can't see beyond. And then for some reason, you're above it and you can see the whole thing and it's all clear now, like free body diagrams, something like that. I don't know. Yeah.
So what fraction of office hours should people go to?
As many as they possibly can. So, depending on your schedule, like I know folks, they may have doctor's appointments and stuff that might not align. Try to go to 100%. That's the goal. 110, create your own office hours. I often did. All right. I would just barge into somebody's office and say, hey, I need help now. Not like that. Obviously, say kindly, be respectful. But yeah, shoot for 100. But obviously, some things come up and you can't make it to all of them. But maybe you can reschedule with them as well. That's a possibility. You can say, hey, I can't make it. Can we find another time? I can guarantee you they're willing to work with you and trying to find a new time to talk with you about something you need to do.
He said, kindly and respect.
Hey, I didn't say that.
I'm not rude.
Yeah, well, sometimes I wasn't the nicest to you either, so I get it.
But it also goes both ways.
Yeah, it does. He gets it back. Yeah.
Why is there a dark matter halo around the neutron star?
Why?
Yeah.
Okay, this happens in a certain part of the regime of the parameter space. So there's 3 parameters one's got to worry about when talking about bosonic dark matter halos, really all dark matter situations. The amount that you got, right, by gravitational mass, the particle mass, and the self-repulsion strength. Okay. So if you dial up the self-repulsion strength, you can easily achieve halos with, many particle masses that you can select. And this, regardless of the amount, you can get a large extended structure. Or, for example, say you fix the particle mass and you fix the halo, and for some amount, you're inside the neutron star. But if you tweak up and add just enough particles, you can extend beyond the surface. So sometimes it relies on the amount that you have in there as well, because there's a self-repulsion. They don't want to get too near each other, right? Although they're bosons, they have that interaction, so they can't fall inside the boson-Stein condensate state, which is a state where all the particles lie in the ground state, the lowest available energy state, which is what you will learn in statistical mechanics. Oh, okay, Mike.
So do we assume then that there would be a dark matter halo around everything, like around us and around the particle, and everything has dark matter halo around it?
Possibly, but we don't have, the other parameters fixed, right? You could have a small amount of dark matter near you. They tend to collect in massive objects, so such as a planet, sun, neutron star. For us, we're so, we're massive with respect to it, but we don't have, we don't worry about protons and stuff too much. Those are on us and stuff. So yeah, there might be some dark matter structure around you, but it's going to be so indetectably faint. There's no way of knowing. And yeah, it also depends on the property of the object as well.
Could you talk a little bit about the sorts of numerical simulations that you're doing in order to build up these equations of state? Are you integrating over the Lambda equation or something like that?
So to build the equations of state, we select what we do here is that we vary the equation of state. So when you vary the equation of state, you allow it to change. So we're not making any new equation state. We have a few. So there's a bunch of the tabulated ones that you can find on the internet. There's a bajillion of them. Or there's other types. So there's a certain type of model known as a polytropic model of equation of state, where you have the pressure is proportional to the density to some adiabatic index. Again, another thermodynamics term. I do a lot of that stuff. So we mentioned. We have a very special model that's been used in a lot of papers, which is a three-piece extended polytrope. So there's three polytropes with varying transition densities, and then there's core equation state. And then we also implement parts of the parameter space where you're near the nuclear saturation density, which is for those who don't know, that's just the number density of atomic nuclei, which is roughly around 0.6 inverse femtometers cubed. So in that regime, we use something known as chiral effective field theory, which is just a model independent way of talking about baryons and working out those equation state from using that framework. So we use a lot for this paper. We just use that one because we can vary the adiabatic index, we can vary the transition densities and cover a large swath of baryonic equations of state. Mm-hmm. Yeah.
I'm just curious also about the parameter F sub chi right there.
Yeah.
Is that your flux?
That is the dark matter mass fraction.
Oh, okay.
Yeah. This is so here in all this is the soft repulsion strength, and here is the mass fraction, and then we have the particle mass there and chi. Yeah. So yeah.
I have a question for when we're all done with physics. I want to be around physics.
You don't have
Are we
to.
happy?
We can switch back and forth.
Okay. So I think it's very impressive that you're in grad school.
Thanks.
Very cool. But I think the most impressive thing about you is probably the strength of character that you have, the tenacity that you have. And I know you sort of briefly spoke about it. Like, are you okay if I mention like a couple more things?
Mm-hmm.
So basically, at a younger age, you were told that you were really bad at math and not really worth teaching.
Indeed.
You came to higher education despite some resistance from your family.
Mhm.
And they were also really critical about you studying science.
Yeah.
You're bold enough to change your major.
Yeah.
And you didn't get into a lot of RUs, but you tried to get into.
Oh yeah, those. Yeah.
And, then you didn't get into graduate school, as you mentioned, but I called you on the phone probably multiple times a week at this time. So I was going through some shit and making you different.
Oh, yeah.
And just every day you were telling me like what you were studying and how you were focusing on learning things you didn't even need to be learning and like practicing for your GRE all over again and like fixing your personal statements and just making your application like top tier for your next try. And that strength of character is something that I think a lot of us like in our group of friends like built here, like at Oneonta, because the whole world isn't at your feet at SUNY Oneonta, and you really need to learn to be like resourceful, like a little bit scrappy, and then you take all these opportunities one at a time, and maybe you don't even know why, you just want to, and suddenly you have this kind of really beautiful mosaic of like self-development and passion for your work. And I know that you really took full advantage of all of these things, so I was hoping maybe, for the sake of students who don't necessarily know if they want to go to grad school, we can all learn something from you at your time here. So maybe you could talk about things outside of the studies that you did in the physics courses and what you really learned from them or how you found them and maybe the mindset that you took when you went through your undergraduate.
Wow, that was a really dense question, but we can attempt to answer this in the time frame that we have because that's like effectively my life story in a way. So when I was younger, I was forced to go to summer school for math. And several teachers said that I wasn't ever going to be good at math and that I should probably quit trying now and go to, we had this BOCES program where you go and like learn something about mechanics or something like that. And I said, no, you're wrong. I think I'm better than that effectively. Although at the time I did believe them because, when you're young, you're very impressionable. Even now you are. And when, folks who are in more established positions say, negative things about you, it can force you to believe that those things might be true. But if you know within your heart of hearts that you are going to do something, then damn it, do it. Okay, regardless of like what it looks like, how pretty or how ugly it gets, you will find a way, I promise, as long as you don't give up and as long as you really love what you're doing. You must love it. Don't do it half-heartedly because it's not going to work. All right, it might work for some time, but eventually it's going to catch up to you and you're going to be, you might feel fairly miserable and wish you did something else. So pick what you love and go for it as if your life depends on it. Not literally, because no, it doesn't, but like put a lot of passion into it, fully immerse yourself in what you're doing. And that's how I found physics, really. Because when that teacher told me I wasn't really worth the time, I said, okay, well, what if I, in my child brain, I, was like, okay, I'm going to find a way to be better at this. I don't care what this teacher says. I'm going to learn this algebra right now. And I'm going to sit here until I figure something out. And that was hours and hours and hours sitting alone because I'm from a working class family. So my dad's a truck driver. My mom works as a secretary. So like they're not very good at math. So I had to sort it out on my own. And that meant, YouTube, that meant Google, that meant just finding any stupid resource that would possibly help me figure something out about this algebra thing I was trying to learn at the time. And then, going forward, as Hannah was mentioning, I again struggled with my family because they're working class. They don't really understand what the STEM fields are like. I convinced them that, maybe chemistry was a good idea because that's something they could visibly see that, oh, a chemist is going to go work in a lab and make these fancy chemicals and that's going to be fine. I could reason with them about that. And that took a lot of research for me to convince them that's what it was. And then I didn't tell them at the time that like, I'm switching my major. I'm going to do this thing called physics. And I don't know what I'm going to do with it, but I don't really care. I've always liked it. I really enjoyed my time in high school with it. And so I went and switched. And then I, again, found trials and tribulations with this thing known as REUs. So if you do want to go to graduate school, one thing you can do to help get yourself in research is apply to these things called research education for undergraduates. You probably want to, if you're going to do it now, you might as well start looking right now because I don't know when the applications are due, but they're due sometime in the winter. You?
Physics and astronomy students in the room. I sent you this week a document on how to search for an REU. You remember getting that? That was written by him.
They're really fun and you get paid.
Yeah, you do get paid to go.
Out of state, travel a bit,
Yeah.
do some friends, do some research, get some money.
I went to California for the one I was accepted to, California State at Chico. It was a really good time. It was stupid hot. You learn about a little bit of areas that are different than, this area or Long Island or wherever you're from. Hannah went to Michigan and Indiana, Midwest, which, is also hot and wild out there, but it's a good time, which I recommend. But they're not also, if you're not looking to do graduate work, there's also internships you can look at. So, there's other sorts of places of work. So you don't have to do these REUs unless you want to go to graduate school. It's a way of testing, a little bit of, you might not do something that, you're really familiar with. So I did something in like applied mathematics, right? I had never done any applied mathematics, but I solved differential equations once before. So maybe I could try it. And they're not really expecting all that much. You're just here to experiment and give it a good whirl. And you get to be around other folks, which is really fun. But there's internships too, in case you don't want to do that after graduate school. You can intern with a company if you want to do some engineering stuff, or I can't name all of them because I'm not that knowledgeable about internships, but there's a lot you can do, and your professors can certainly help you out with those. They know a lot of places, and they can help you sort out your application, because writing, again, very important. This is where you're going to have to convince someone to say, hey, I got to pay this person who doesn't know very much. Why are they the best person to hire? Because there's a bunch, like 20 other people who are going to say the same exact thing. So what can you do to make yourself stand out, right? And the one thing I had was passion. I love what I do. I really do. And I love talking about it with other people. That's why I'm here. And I'm taking the time out of my busy schedule, and so are the alum who want to hear me talk for some strange reason, to listen to it. So yeah, I think that's where I was going to end with that in that way. So be passionate, have the passion, or find something that makes you stick out. And passion is a good way. Everyone can have it. You don't need to be particularly talented to have it. You don't need to be great. You can be really, you can have a rough time with physics. It doesn't really matter. But as long as you love what you do, that can come across to other people, and they can really see that you mean it when you say it. And they can really see that, you know, if this person sticks with it, they're going to do something, whatever it is, no matter how big, no matter how small, they all matter. And so, you know, everyone can have it. And I highly encourage all of you to, you know, if you're not already, fully immerse yourself in something that you're truly passionate about, and see where it takes you. Is there going to be struggle along that path? 100%. Some more than others, but that's okay. That's all part of it. It's a little bit of character development is what I call my story. It turned me into who I am, add a little grit to my attitude. So now when someone says I can't do something, I just, you know, shrug them off, and I'm just going to, you know, rip you apart after that. You know, metaphorically speaking, not physically, I'm not going to rip them apart. But, you know, they say, you know, they might be better at me than something. I'm like, okay, let's try it. Let's go for it. Let's do it. And, you know, go all the way and prove a point and really see who's, you know, who's who, you know. So, yeah. I don't know. Was that a good answer to your question?
It definitely answers the mindset.
My motivational speech here. Any other last minute questions? None from the students in the room. Did I scare you all? I mean, it's okay if I did. Oh, I did. You're right. I did get one, but one's an odd number, and that's prime.
I don't exist.
We don't really like prime numbers. No, one isn't prime. Sorry. See, I was a math major. I messed up right there. See, I answered something and it's not prime. Okay.
We tried.
Yeah, well, I hope you know, this talk was worth it for some, if not all of you, in one way or another. And yeah, if you ever want to reach out, I can bring back my slide on my email if you want it. And we can have discussions when we both can work out the time.
It's very well presented.
Thank you. Appreciate it.
Good talk.
Thank you.
If you think Nathan gave a great talk, let's give him a hand.
Okay.
So before we adjourn, also, Nathan left his contact information. All of our speakers have. Remember, this is for you guys too. There is off the department website is a description and bios from all the talks we've had. We're up to about 60% of videos recorded. So they're actually a good resource because it spans everything from someone who's doing research in psychology after leaving the Space Science Telescope Institute to someone who stayed in the Space Science Telescope Institute. So, and then I would like to thank all the attendees. And by the way, Nina's thing is also on the chemistry website, and it's a very valuable tool. So those who didn't get an email from me today are not on the physics or astronomy listserv. Let me know and I'll send them to you. And for you guys, not just REUs, the college funded 30 those students over the summer.
Give or take.
Yeah, roughly 30 students this summer, paying them, they got free housing, which they used to do, and paid $3,000 for 6 to 8 week programs. So if you can convince a faculty to work on something over the summer and tolerate you, then those are pretty readily had. No, I love you too, Christine. What did you mean by that? You know, you're so mean to me. I still stand. Thank you all for your time. Really appreciate it. It's good for you.
At the end of the day.
Isn't that right, Nathan?
What?
You like to see everyone here?
Yeah, they do. That's why I invited my little group. All right.
That was awesome.
Thanks. Appreciate it.
I appreciate you coming here, and I think that
I'm here for physics club. Can I get a picture of you with the professors from the department?
Yeah. Do you want the pass? I was the president of the club.
Oh, were you?
Yeah, do you want the pass president too?
Sure.
Mitch, you want to answer? Want a picture? Past president. Stop.
So is the recording stopped?
I do not know.
She wants to do a picture.
Yeah, it looks like it was stopped recording here.
Like we.
Stopping it here.
I do want.